Hello and welcome back. My name is Callum and today we'll be covering modulo arithmetic. Modulo arithmetic is very important when it comes to cybersecurity. The laws of and properties of modulo arithmetic is what makes RSA work, the leading encryption in everything nowadays. So it is very important for us to understand how those properties are used and how to utilize them, for example, to answer these questions. So I've written a few mock questions in front of us just to work out and see how we use these theorems and how to get a better appreciation of how to remember them. So the three theorems that we're going to be using are the simple law of exponents, where a to the power of m times a to the power of n equals a to the power of m plus n. This will be very important when breaking down questions later on. The laws of modulo arithmetic. So modulo means when you divide up a number and you take the remainder. For example, 12 mod 5, you try and divide 12 by 5, you can do it twice with a remainder of 2. So this equals 2. And of course, 10 modulo 5 has no remainder because it evenly divides into it, meaning the answer is 0. So the laws of modulo arithmetic state that if you have two numbers times together, modulo n being anything, what you can do is you can modulo the numbers individually first and then mod the summation, or the product in this case, to get the answer quicker. We can do this for anything. For this example we're using timesing, but we can do this for dividing, addition and subtraction as well. And this will be useful for this second question here. And the third theorem is Fermat's little theorem, stating that if a is a positive integer and p is prime, then a to the power of p mod p equals a mod p. This is going to be very useful once again for this first question. So let's crack on with answering them. Let's look at this first question. The number 2863 is prime. Already you can start to see where this third theorem can be useful, because we see that there is prime here. So it should start the bells ringing. Calculate 5 to the power of 6865 mod 6863. Well, there's a lot of numbers, but once again, we're not allowed calculators in these questions, at least in our examinations for these kind of questions. So the first thing that we need to do is make this equation be able to be plugged into Fermat's little theorem. Because right now, P is 6863, but the power, the exponent here is 6865. So we need to split that out. So we can split that out by simply, using the power of the laws of exponents here. Not only can we get m times a to the m times a to the n equals a to the m plus n, we can take them apart. So as much as we can add them together, we can split them apart. So we can get 5 to the power of 2 times by 5 to the power of 6863. Because once again, we can see that timesing these two together, because the bases are the same and the exponents are different, or the exponents don't have to be different, but the exponents add. So we know that this equates to 5 to the power of 6865. We know this. So we can split it apart, but the reason we're using this is so that when we modulo 6863, you can see that this condition now matches Fermat's little theorem, meaning that we can get rid of the power from the exponent from this side of the equation. Still, we're keeping the first bit. So 5 to the power 2 times by 5 mod 6863, that should be. But we are getting rid of this exponent by using what we know about Fermat's little theorem, where a to the p mod p equals a mod p. as long as p is prime. So we've simplified that down, and now we can sum up our parts again. So once again, 5 to the power of 1, because the exponent is assumed. So this actually equals 5 to the power of 3 mod 6863. And of course, trying to divide 5 to the power of 3, which is 125, by 6,863, the remainder is 125, because you can divide it in there 0 times. So the remainder is 125, and that is the answer. The answer to the question, what is 5 to the power of 6,865 mod 6863, is 125, using those methods. And we know that's right, because we have used the theorems that were shown. So that is a little bit complicated. You have to divide out the question and put it back together, but that is not too hard to learn. On to the next question. Calculate two very big numbers, mod 100. We can use the laws of modular arithmetic here, and we can split this up. So simply we can do 1, 2, 3, 2, 4, 8. Oh my god, very big number. But we know mod 100. Mod 100 is if you try and divide something by 100 and what you're left over. And you know that something is a multiple of 100 if their last two digits are 0. So if their last two digits are not 0 and they're a little bit above 0, then that will be the remainder that's left over after you divide by 100. So for this number, it's a very big number, and we could try and calculate it and do a long division and actually try and divide it. But we know that if we divide this by 100, the remainder will be 5. Definitely. Because if you try and divide that long number by 100, the little bit extra that is remaining in the last two digits are what is left. And we know that is 5. And we know that if we type out this next answer, or this next question, sorry. Once again, the same thing applies. You take the last two digits, because if you try and divide this big number by 100, the little bit left over is the remainder. So 11. And because of the law of modular arithmetic, all of this big multiplication, mod 100, you can mod the two numbers individually, and then you can just times the numbers together and then mod 100. So the two numbers times together is obviously 55, and if you try and divide 55 by 100, it goes into it 0 times, but 55 left over, so 55 is the answer. That is very simple. Even though there are very big numbers, you could calculate them all by hand, but if you don't have a calculator, this is a very, very quick and easy way to answer that question. And now, for the next question, calculate 7 to the power of 48 mod 11. Now, with this question, I like to use a bit of a trick, because, once again, you could try and calculate this out and, make a big, large calculation, but here's the trick that I use. Because we know that, once again, due to the law of exponents, 7 to the power of 48 equals 7 to the power of 32 times 7 to the power of 16. Right? We know this. So if we start calculating from the bottom and work our way up, we can start calculating what it requires. So let me show you. Let's start with 7 to the power of 1, mod 11. Right? 7 to the power of 1 is obviously 7. And 7 mod 11 is 7. Because if you try and divide 7 by 11, it doesn't go into it, and there's a remainder of 7. Now, 7 to the power of 2, hear me out here. Instead of writing it, because once again we know 7 squared is 49, but just for now, we're going to times the answer of the previous question. So we know that 7 to the power of 2 is 7 to the power of 1 times by 7 to the power of 1 mod 11, which equals 7 times 7 mod 11. And once again, we know that because of the law of arithmetic, what we're doing is we're using the modding of each side of the times table here, where we are reducing it to its lowest form. So doing this calculation, we're doing 49 mod 11 now. And 49 mod 11, once again, if you try and divide 49 by 11, you get 44. And then the remainder is 5. So we can put a 5 here. And now we go one deeper. Mod power of 4. And it is the power of 2 times the 7 to the power of 2 mod 11. And we know, because of this answer here, we could do 49 times 49 and do that big equation. Or, because it's already modular and we know we're doing it by modulo 11, we can do this. And we can use the answer from the previous question. So we do 5 times 5 mod 11. And we know 5 times 5 is 25. And that's much easier to calculate. And 25 mod 11, you divide 25 by 11, you get 22 and a remainder of 3. And you can do it again. Power of 8 mod 11, which is just 7 to the power of 4 times 7 to the power of 4 mod 11, which, taking the answer from the previous question, 3 times 3 mod 11 equals 9 mod 11. That equals 9. And we can keep going. And we got 7 to the power of 16 mod 11, which is 7 to the power of 8 times by 7 to the power of 8 mod 11, which is 9 times 9 mod 11, which equals 81. 81 mod 11. 77. And we take the what's left over, and what's left over is 4. And then get up to mod 11 to the power of 32, and we can once again substitute 16 times 7 to the power of 16, which is 4 times 4 mod 11 equals 16 mod 11, which of course goes into it once with a remainder of 5. And wait, we know that 7 to the power of 48 is just 7 to the power of 32 times 7 to the power of 16. So we can do 7 to the power of 42, or 48, sorry, mod 11 equals 7 to the power of 32 times by 7 to the power of 16 mod 11. And we know that mod 16 is 4 and mod 32 is 5. So it's just 5 times 4 mod 11. And 5 times 4 is 20. 11 goes into it, and then the remainder is 9. So the answer to 7 to the power of 48 mod 11, the remainder would be 9. And we know that because we've done all this working out and we calculated it, we've gotten down, and once again, these just using the laws of exponents. Because you know that the 7 to the power of 4 is 7 to the power of 2 times by 7 to the power of 2. And modular arithmetic says that we can do the modulo and then use that answer in the following times table. So we know that. And that's how you would answer that kind of question. Hopefully that makes sense. If this has been helpful to you at all, please like and subscribe to my channel. And please let me know what you would like me to cover next. Thank you.